All right. All right, so this section, we're starting on section 10.4. We're going to start on page 70, I think it's 74, yeah, today, because it doesn't make sense to do it in the order that they had it. So we're gonna do it here. I may go a little bit kind of out of order, but we'll get to the point eventually. Let me see if I can do it this way. I'm going to see if I can, oops. Let's see if I can just do this. I think I could do it better with the comment button. There we go. I think I got it. I'm going to try it this way. If it doesn't work, I'll let you know. All right, so the idea behind logs is logs are functions like anything else, like exponentials. They have certain rules that you can use, and you have to adhere to the rules. So, and the point is square roots have their own rules, right? So what I mean by square root, I've got this little radical thing here, right? It has a square root. So if I wanted to evaluate the square root of 9, I know that the square root of 9 is 3, right? Because 3 times 3 is 9. Now, I know the square root of 4. The square root of 4 is 2, right? Okay. Now, the question is, what's the square root of 5? Well, I don't know the square root of 5 because nothing squared I know is 5. So I'm going to use my calculator. I'm going to pull my, oh, I got a, did I record? Yes. All right. So I'm going to calculator, turn this on, and I'm going to hit the square root of 5. And I get 2.236-ish. All right. So the question they ask you, does the square root of 9 minus the square root of 4 equal the square root of 5? So the square root of 9 is 3. The square root of 4 we found was 2. And the square root of 5, the question is that equal 2.236? And the answer is absolutely not, right? So the point is that you can't just subtract square roots. So this is a really common algebra problem that you run into. The square root of x minus y, it does not equal the square root of x minus the square root of y. So there's no way that's going to happen because it's just not a rule for square roots. The only rules for square roots you have is, if you remember, you have a product rule. The square root of a times b is the square root of a times the square root of b, and the square root of a over b is the square root of a over the square root of b. So these are really the only applicable rules that you have are these two. There's no rules for sums or products. So the point is you have to follow whatever the rules are. Here she's trying to cancel square root signs. So can you subtract away square root signs? Absolutely not, right? Because the square root of 9 is 3, the square root of 4 is 2. And that does not equal 9 minus 4. So square root signs don't cancel. All right, they're their own separate thing. All right, just like logs don't cancel. And there's going to be certain rules that we're going to use for logs. All right. I'm not sure why she's doing this, but with a square root, the square root of 25 is 5. So that's 5 minus 1 is 4. All right, and then like here I have 3 times the square root of 1 minus 1. Well, the square root of 1 is 1, so it's just 2. All right. The question is, can you cancel square root symbols? Well, the square root of 81 is 9, and the square root of 9 is 3, and that equals 3. Whereas 81 over 9, that equals 9. So you can't just cancel square root symbols. All right, and the same is true for logs. This is what she's heading toward. If I have the log of x over the log of 3, we don't know what a log is yet. You cannot cancel them. All right, so no, there's a separate rule that we're going to learn for logs. All right, so the point is, just like square roots have their own rules, so do logs, and we're going to learn them. All right, so a log, we're gonna do some of this on the calculator, and then we're going to talk about what a log is. I mean, I would rather talk about what it is first, but they're basically what a log is. They're the inverse of exponents. So a log is something that undoes an exponent. So for example, if I take 3 and I get 9, and then if then to undo that, I would take the square root of 9 is 3. So in a sense, a square and a square root are inverse functions because they undo each other, right? So a log undoes an exponent. All right, that's what it does. And we're going to talk about that in a little bit. Right now, we're just going to show some calculator stuff. All right, so if I want to evaluate log of 10, if you look at your calculator, there's 2 log buttons. There's actually 3 that we're going to learn about today, but there's 2 out here. Log is what we call log base 10. That's called a common log. And log base E is called the ln, which we'll talk about. It's the natural log, all right? There are other logs, all right, with different bases. All right, the base can be any positive number. We need to talk about what that means, okay? But I want you to see those buttons. So if I want the log of 5, that's pretty much this log, I can plug it in a calculator. So log of 5 is 0.69, now I'll just say 0.7, right? That's about 0.7. All right, now if I do the log of 8 minus the log of 3, I'm going to plug it in the calculator. Just like so, and I get 0.426. So the question is, does this, which is 0.426, equal to log of 5? The answer is no. So you cannot subtract these numbers and make it a 5. There's no rule for that, okay? So we have to know what the log rules are, all right? And this is obviously false too. You can't subtract away the logs in front of them because log 8 minus log 3 was 0.426, right? And that does not equal 5. So what can you do with logs? We're going to learn about that today. Okay, so the point is they have their own rules. And we're going to get there. All right, so your calculator, what is a log? And that's what I don't like, but I'm going to talk about it just a little bit here. I'm going to say it's log base A of B, all right? It's the inverse of an exponential, the way that, let's say that equals C, whatever it equals, right? With exponents, I'm saying A to the C equals B. So I'm saying to what power do I have to raise A to get C? So you think of B as, what's the exponent? Okay, so what I'm asking you is the power C. A to what power, right, equals B? That's really what you're asking. All right, and we'll deal with some numbers. It's better to deal with numbers, but I want you to understand logs have bases, all right? And this base here is the base of the exponent. And there's a log, there's two different types of logs. If log is implied to be a base 10, okay? And they don't write the 10. It's kind of like a square root. They don't write the 1/2. So log is what we call base 10. So if I say the log of x equals y, I can write this as an exponent. I think there's a 10 here. I just don't know it. I would say 10 to the y equals x. All right. So log base 10 is undoing an exponent with base 10. All right. Another type of log is log base E. Now, E is a number, it's 2.718, but we don't write log base E, all right? They don't write that. What they write is they write ln, all right? And an ln undoes an E. So this undoes E to the y equals x, okay? Remember, E is like 2.718. And this is called a natural log. That's the word that's the end there, natural log. And this is called a common log. So this is what we call the common log, and this is what they call the natural. Okay, anything else is just a log. In calculus, more often than not, and anything else, use ln's because they're easy to work with, believe it or not. But we're gonna find some logs on the calculator, and so I'm just gonna do that real quick. So if I want an log, that's the common log. That's this one. I'm just gonna type the numbers in. So the log of 10 is 1. The log of 1 is 0. Log of 8 is 0.903, and the log of 800. Okay, so a couple things I want you to notice. Log of 10 is 1, because pretty much I know that 10 to the first power equals 10, right? All right. The log of 1 is 0. If I write this exponentially, the base is 10, so I know that 10 to the 0 equals 1. So see how the logs are pretty much just the exponents, all right? Log of 8 was, what was log of 8? I forgot. 0.903. which pretty much tells me 10 to the 0.903 is 8. That's what it's telling me. And the log of 800 was 2.9. So this tells me that 10 to the 2.9 is about 800. Okay, so a couple things I want you to notice. The log of 1, well, we're going to talk about that. Let's go here. You know, I take the log of 8 is 0.9. The log of 800 is 2.9. So this is going up, but very slowly. Okay, so that's something to keep in mind. I'm going to go over here for these guys since all right, I'm just going to plug it in the calculator with the LN button now. So the ln of E is right here. It's also here. I'm going to use this one. The ln of E is 1 because it's log base E. The ln of 1 is 0. The ln of 8 . So I'll do 800 while I'm at it. All right, 2.08, 6.68. So you see it goes up, but not too fast. I think it was something like that. All right, so a couple, oh, this is 0. Okay, sorry, I have to fix that. That was 0. All right, one thing I want you to notice here. I don't care what the base of the log is. One thing that you really want to kind of know is the log of 1 is always 0. And that makes total sense because no matter what the base is, if I raise anything to the 0th power, I get 1. So the log of 1 is always 0. Okay, so that's something to know. I don't care what the base is. All right, before I get into this, there are other bases of logs. Okay, and we're going to do some practice, but I want you to know that there's more than just this. I can do the log base 10 of 5, which would be like that. I can do the ln of 5. I can also do log, I can do any power of 1. So if I do log base 3 of 5, okay, so here I'm saying, basically what I'm saying when I evaluate this, I'm saying 10 to what power equals 5. Here it's base E, so it's E to what power equals 5. And here it'd be 3 to what power equals 5. All right, so whatever the base is, that's the base of the exponent, okay? Now, your calculator can evaluate this. If you have a TI-84, all right, if you have an 83, hold on a second, we'll talk about how to do this. All right, if you get your TI-84, your Inspire out, there is a log-based button added to the new operating system. A couple ways to get it. You can go to Alpha F2, that's how I do it. You see number 5, it says log base. So if I pick number 5, so alpha window 5, I can just type it log base 3 of 5. It's 1.46, whatever. So if it's telling me that 3 to that power should be 5-ish, because I rounded. All right. So remember that the log is what's the exponent that I'm raising it to from that base. All right, so your calculator, another way to get to that button, if you hit math and just scroll down to A, so there it is, log base, and I can just do the same thing. All right, so your calculator has the ability to do logs of different bases, okay? You have the LOG button is base 10 and the LN button is base E, but if you need another base, you got to go to these other buttons, okay? If you have an 83, we'll talk about how to adjust for that. Okay, in a bit. All right, we give it that? Yeah. All right. All right, so evaluating these things is the same thing as just plugging numbers into the calculator. You learned this is X, right? So you're just going to plug in X as 6. I'm just replacing X with 6, and that's just something I can type in my calculator. So if I pull up my calculator, I'm just going to type that in. 12.4 And now there's an e to the x button right above the ln. E to the, what is that, 0.2, that should be a 0.2 times 6. Notice how what I'm typing stays in the exponent. It'll stay there until I arrow out of it. So I'm going to hit the arrow button to get the 5 downstairs. Plus 5. And there it is. I get 46.169-ish. All right. So, and I can do the same thing. I can evaluate logs. This is a common log. It's base 10. So I just plug the number in, the 15 there. So log 15 minus 5 plus 20. So again, I can just plug this in Mr. Calculator. 125 log 15 minus 5, close that parenthesis, plus 20. And I get 145. Okay, all right. All right, everybody able to find their log button? Okay, if you have an 83, hang on, I'm not done yet. All right, your calculator can graph exponential and log functions. Some things to keep in mind. Exponential functions will either look, they'll always have a horizontal asymptote, usually positive, and this is what they, well, there's growth and there's decay, but one way or another, they'll look something like this. In log functions, we'll have a vertical asymptote, usually it's 0, and they go like this. They go up and down. So just something to keep in mind. So when you're graphing that, you want to see something that looks like that. So I'm going to type this function in my calculator in the y equals button and graph it. All right, so this is 12.4. E to the 0.2x plus 5. Let's go downstairs. All right, so if I just use a regular window, this doesn't look too good. I know what it should look like. It should look something like this. It's going up. So I don't have a good window. All right. Now there's a couple of ways to deal with it. What I personally like is I'm going to keep these X's. I want to change the Y's. So what I'm going to do, if you hit zoom fit, what zoom fit does is it doesn't change X, but it fits the Y's to whatever window you have. So I'm going to hit zoom fit. And now I have a nice graph that looks like what I expect. It's got that exponential curve to it. All right. A couple things to be aware of. If you go, let's go to the table. If you go to negative X's, if you keep going down and down and down, it doesn't go negative ever. In fact, in this graph, if I go to second table set, I'm going to go to negative 100. Maybe 100. I want you to see what happens as X gets really negative. Let me go to the table. As X gets really negative, see why it's heading toward 5. It's never going to equal 5 but the calculator rounds it to 5, but it's never going to equal 5. It's just always heading to 5. So that helps me with my graph because I know that here's 5 and exponentials always have horizontal asymptotes. I should have drawn that on here. All right. They'll never cross that line. So in this particular case, it has a horizontal asymptote at 5 and it looks something like this, right? I mean, after that, it doesn't really matter, but I can find a couple points if I wanted to, but just to see that it has that growth. All right. So the window that I'm using, that's a good window. Let me go to my window. All right, I'm going to fix the X's. Fix the Y's. I'm going to let Y min be 0 and let Y max be 100 just to make them nice and pretty. All right, and so I have a pretty nice graph there. Okay. It doesn't have to be like, I could do anything I wanted there, but okay, but that's a nice window. All right. So I did negative 10 to 10 and 0 to 100. All right. So when you go, you can graph logs on the calculator, just type them in Y equals. So So I'm going to go type this other example. 125 log log of x minus 5 plus 20. All right, I'm just going to try the window I have. All right, so what I want you to notice is, logs should kind of look like this. So I'm missing a little bit of x, and I don't need all this negative x down here. So I'm gonna let x start at 0 instead. I'll go from 0 to 20. All right, and then we'll take a look, see how it looks. All right, I'm starting to see the curve, not that much, but I want to see the negative part too. So let's change the window. Let's keep the window where it is, and let's do zoom fit. Show you what that does. Zoom fit. All right, now it has a nice window where I can kind of see the shape of the log. All right, this is what it should look like. I can see it crosses and it goes negative, and there's a vertical asymptote with 5 that it will not cross. All right, so if you go to the table, let's go to the table. Actually, let me change my table here. Start at 0. All right, so if I go to the table, see any number 5 or less is an error. So that's where your vertical asymptote is at 5. All right, so nothing crosses this thing. So this graph pretty much, I'm just drawing a sketch. And there's my asymptote at 5. And it looks something like this. Okay, so the window that I had, this window. All right, again, I'm going to change these, make them look a little pretty. I'll call that -80. And then I'll just call that, that's really big. Let's call it 170, I guess, just to clean it up. Yeah, that's fine. All right, so I went 0 to 20 and -80 to 170. Lots of options there with your window, but you want to be able to see that shape of the graph when you graph them. All right, is that all right? Okay. What we need to talk about is domain. All right, so domain, there is an issue with fractions and square roots. There's also an issue with logs. All right, so this kind of completes the domain for you guys. So if I look at this graph, this is the graph of 2 to the x. It's flat and then it goes up. This is called growth, exponential growth. And I want you to notice that this graph does not dip below 0. So it has a horizontal asymptote at y equals 0. And this graph also does too. This is 2 to the negative x. When the exponent is negative, it's called decay. All right, so it just kind of, instead of going up, it goes down. Let me get rid of this. All right, that didn't work. All right, let's try it again. There's a horizontal asymptote at 0. So horizontal asymptote at y equals 0. And this is growth. This is decay. Okay. But what I want you to notice is the domain and range are the same no matter what. The domain of this, it goes from negative infinity, it goes up and out forever. So it goes from negative infinity to infinity. It's all real numbers. And the range is what's interesting. The range, the exponent's only good for greater than 0. It can't even equal 0. So the range is from 0 to infinity. Okay. Just looking at those graphs. All right. So just to convince you, she has 2 to the x. If we type that into the calculator, and I can go to the table, and if I have an answer there, it's in the domain. So, if I look at -2, yeah, there's a value. It's 0.25. If So look at -1, 0, 1, 2, 3. Look at all that. You see there's values all the way through. So yeah, they're all in the domain, right? Because they got values. The domain is all real numbers, so it's no shocker. 4.5, you know, you could do it this way. You could graph it. You can see there's a value there, but if you're not sure, second trace. Well, second trace, I want value. I'm going to tell them X is 4.5. Can I get an answer? Hopefully. Right, so it's in the domain, or 3.5, it doesn't matter. So the whole point is the domain of exponentials are negative infinity to infinity. When you look at your calculator, I want you to notice that all the numbers are positive. All right, there's no negatives. See how it just gets smaller and smaller and smaller as we get negatives. So there's the range is 0 to infinity. All right, and that's true of all exponentials. So how does that fit? Oh, these are yeses. I'm sorry. She's got it's every real number, right? It can be anything we want. Okay. All right. So how does that fit with logarithms? All right. Well, a logarithm is the inverse of an exponential. The way that you find an inverse is you switch x and y. So if I want to find the inverse becomes the point yx. All right. So if you think about it, the domain and the range should flip-flop. All right. So if you look at these graphs, she has a few graphs there of logs. By the way, you can graph those on the calculator just to show you a graph of a log. If I want to graph log base 2 of x, I go to alpha window, log base. I'll graph it. All right, so you can graph logs in your calculator. It's not a great window, so let me try something else. Doesn't look good. So zoom fit. Now it looks better. All right, remember this goes down all the way. On some calculators, it's going to look like this thing crosses the x-axis or the y-axis. It does not cross. It goes down forever. That's your vertical asymptote. Let me kind of make this so you can see it. Let's go -5. See if it'll go down. We can look at it. See, it looks like it touches. It doesn't touch. It goes all the way down to infinity. All right. So the logs have a vertical asymptote at 0. Doesn't cross it. I'll just say vertical asymptote at x equals 0. All right. So when I look at the domain, and she's got some different bases here. If they have a big number bigger than 1, they're going to look like the red graph. If they have a number less than 1, they're going to look like the blue and the green graph. The base can't be negative. The base can't be 0. Those are no-nos. So if what was I going to say? Oh, if I look at the domain of this graph, for the logs, it starts at 0, not including 0, and it goes out to infinity for all of them, right? And the range, it goes down forever and up forever, so the range is all real numbers. So what I'm trying to get you to notice is that with the exponential graph that we had just done, the domain was all reals and the range was 0 to infinity. So pretty much because I flipped x and y and domain is x and range is y, the domain and range flip-flop. So the range became the domain and the domain became the range. All right. So that's just kind of a property of inverse functions. All right. So I just want you to see that logs, the main thing here is when you're taking a log of something, it has to be greater than 0. You cannot take the log of 0. You cannot take the log of a negative number. That is not possible. Okay. So no logs of 0 or negative numbers. Okay. So logs have a restriction in the domain. Remember, we had done fractions and square roots. Now we're adding logs to our list of restrictions. So logs not defined for negatives or for 0. So it has to be strictly positive. She's got the graph here. You can see this is the table of it from the calculator. You can see from 0 down, these are all errors. So these are not in the domain, right? but these guys are, right? And actually, you have to check 0.5. Anything bigger than 0 is going to work. Like fractions work, but not anything less, 0 or less. Okay. All right. So one of the things to keep in mind, and I'm gonna do it this way before I do it in the calculator. So whatever's in the log, you can't take the log of a negative, so it has to be greater than 0. All right, so if I set whatever in there greater than 0, and I move the 2 over, I get x is greater than 2. So this tells me the domain of this should be every number bigger than 2. All right, so let's take a look at this. So I'm going to graph it. Log of x minus 2. That's a common log, so we're going to use LOG. I graph it. Just want to show you the graph. Yeah, it looks like a log. Now remember, this doesn't stop. It goes down forever at 2. You just can't see it. So if you go to the table, you can see that anything from 2 down is not in the domain, and from 2 up is pretty good, I hope. See, all those are errors from 2 down, and anything bigger than 2 will work. All right. And you could do anything you want bigger than 2, like just to show you, here's my graph. I can evaluate it at 2.0001. As long as it's bigger than 2, it's going to have a value. Okay. All right. So the questions I have to answer is 0 in the domain? That's a no, because I know it's anything bigger than 2. 1, no. 2, no, not 2, because that's 0. And then anything bigger than 2, yeah, it's in the domain. Okay. So you have to keep in mind that with logs, what I'm going to tell you, when you have, I don't care what the base is, LOG, LN, whatever it is, when you have the log of a function, the domain is going to be that the function has to be greater than 0. Okay. So whatever's in those parentheses has to be greater than 0. That's how you find the domain of a log. Okay. All right. Important, no negative numbers. You cannot take the log of 0. All right. The argument of the log function must be greater than 0. The argument is the thing inside the parentheses. The argument is the thing inside the parentheses. So the log of whatever it is, has to be greater than 0. Okay. Now, here's the TI-84 to do the log-based button. Remember, you can do, just to show you, if I in my calculator, if I do, let's do log-based 2, so I hit alpha, alpha window, log-base. Let's do log-base 2 of -5. What happens when you plug in a negative number? Well, let's take a look. All right, you're going to get an error, okay, because that's not, you're not allowed to take logs of negatives. So when you get that, it's because it's not allowed to happen, okay? If you try to take the log of 0, you're also going to get an error. It has to be a positive number. Yeah. All right. And the other thing is the base of the log has to be positive. It could be a fraction, but it has to be positive, just to show you what happens when you do a negative number. I'll do log base -2 of 6. Should get an error. Yeah. Okay. So no negative bases, no negative numbers. Okay. All right. Okay. Now, what happens if I have an 83? 83s don't have that button. So you have to do it the old. All right. So if you have an 83, what you're going to do, if I want to evaluate, she's got an example there, but I'm going to do my own. Let's say I wanted to evaluate the log base 3 of 6. All right. Your calculator does not have a log base button if you have a TI-83. So what you basically do is you need to take the log of 6, the big number, over the log of the base. The way that I remember this formula, base goes on the bottom. So the 3 goes on the bottom. So in my calculator, I can take the log of 6 and divide it by the log of 3. All right, and there's my answer. All right, if I have the TI-84, all I have to do is the log base button, which is 5. Log base 3 of 6. I should get the same number. And there it is, okay? Now, if you have the 83, you can also do the same thing. You can take the ln of 6 over the ln of 3. It doesn't matter what log you use. You're going to get the same answer. So if I do the ln of 6, just to show you. All right, I get the same answer, okay? So if you have an 83, that's what you're using, that change of base formula. Other than that, I don't think you're going to need it if you have the 84. Okay. All right, so that's that. All right, so if I want to evaluate these, you guys go ahead and try these with your calculator. Either do the log base button or do, you know, the old-fashioned way would be the log of 11 over the log of 4. I don't care. Just make sure you can do it. I'll do it the TI-83 way. And I end up getting 1.73-ish. And that's fine. If the base is a decimal, that's fine, as long as it's not negative. So the old-fashioned way is the log of 6.25 over the log of 0.5. And I'll just type it in my 83. All right, I get negative 2.64. A log can be negative. You just can't take the log of a negative. All right. And we'll do log base 12 at 2. We'll do that the new fashioned way. So if I have an 84 alpha window, log base, what is it? Log base 12 at 2. I have 0.279. All right. All right, so as long as you can evaluate a log on your calculator, you're good. All right. So when you're finding the logs, when you're finding the, what do you call it, the domain of log functions, you know, if I had the ln of x plus 5 and I wanted its domain, all I have to do is set the inside greater than 0. So if they set x plus 5 greater than 0, you have to solve it, right? So you're going to minus the 5, so I get x is greater than negative 5. All right. And on a number line, that would look like this. So with bracket notation or interval notation, you're going to go from negative 5 to infinity. All right, round brackets with logs. All right, we exclude negative 5 because that's 0. All right, remember when you have an inequality, there is one situation in which you flip the sign when you multiply or divide by a negative. So for example, if I'm working with this, I can move the 5 over. And then I could divide by negative 1. But when I divide by negative 1, I must flip the sign. So I really get x is less than 5. Okay. Because I do multiply or divide by negative, you always flip the sign. X is less than 5 goes like this. Here's 5. Here's negative infinity. So with interval notation, it's negative infinity to 5. All right. Is that all right? Okay. 2x minus 3, again, if I want to solve that, I'm going to move the 3 over and make it positive. Then divide by 2. My x is greater than 3/2. Okay, and we are going from 3/2 up to infinity. So the domain would be 3/2 to infinity. Yeah, one point I want to make with the negatives, if you don't like dividing by negative, then don't. I mean, I can move the 3x over rather than the 9 and make it positive 3x. The reason I would do that, then I divide by a positive 3, I'm not having to flip the inequality. So if I divide by 3, see, I don't have to flip it. Now, the inequality is written backwards of what you're used to seeing. So if you want to flip it around, you can. The way that you do that, remember the alligator opens to the 3, so the alligator needs to open to the 3, right? So it says x is less than 3. Here's 3. Now we're going down and starting at negative infinity. So my domain would be from negative infinity to 3. All right. Make sure you write these always going from left to right. 3 to negative infinity is not a right answer. Negative infinity to 3 is. All right, you guys doing all right? Yeah, okay. I feel like I'm talking to myself, which kind of bothers me a little bit, but yeah. All right. So there's your inequalities. Now, this is what I saw one final problem on the final of 13 of our class on this. So I want you to be aware that there may be a log problem on there. So the way that I convert, she's got a lot of words here, but basically to convert from exponential to log form, all right, you're basically writing the inverse. So what you do is I want to include a base. So if I want to convert this to log form, I'm going to write a log. What I say is keep the base. Always look at the base first and then switch x and y. Okay, because that's really what you're doing with an inverse function. So the base of this is the bottom number. The base of this is 5. So I say log base 5 of the other number, 25 equals x. All right, so that's how I do it. I keep the base and I switch x and y. She's got kind of a wordy explanation there. So keep the base, switch y and x. So for example, all right, if I want to write these as a log form, that means I need a LOG. I keep the base. The base in this case is the number on the bottom. So it's log base 2, and then I switch these guys. Log base 2 of 8 equals 3, and that would be the logarithmic form of that expression. Okay, keep the base, switch x and y. So this next one, the base is 3, that goes downstairs, and I switch these guys. So log base 3 of 9 equals 2. That's how I write it. Keep the base, switch x and y. So even if the base is an x, you're still going to do the same thing. So the base in this case is x. So it's log base x of 10 equals 4. Okay, so I kept the base and I switched x and y to write them as logs. Okay. What's the base here on this guy?
7.
Yeah, so log base 7 of 8, right, equals x. So keep the base, switch x and y all the time. Now, once you notice, this is one, well, we'll talk about, all right, so if I do log base here's 4 of x equals 3. Keep the base, switch x and y. Now, here's one little issue you want to be aware of. You can solve this by taking a cube root or by plugging it on the calculator. Right, and we'll do that. Here's why you can't use a log to solve this. So I do log base, the base is x, of -4 equals 3. Do you see what the problem is? What's the one rule about logs?
It can't be negative.
It can't be negative, right? So if you try to take the log of -4 in your calculator, it's not going to work. So this is not a problem that you can use logs with, all right? Logs don't work for everything. What I could do is take the cube root to get rid of it, or I could just plug it in my calculator. You know, remember we did you can solve any equation on a calculator. Once I get the calculator up, let's try it again. There we go. All right, so you know, if I can't solve it with logs, you know what I could do is to solve it like I normally do, go into y equals and type each side. So I could have x cubed on one side and -4 on the other, and see if there's a solution. There it is. So where the blue and the red lines cross are my solution, right? So I can just hit second trace, intersect, 5. Enter, enter, enter. And I get a solution of negative 1.59. So the point is that logs don't work with everything, all right? And this is not something you want to use a log with because the x is in the base, all right? You use logs when you have x's in the exponent. So like something like this, yes, because I could solve that on a calculator. I could do log base 7 of x. Something like this with the x downstairs, no. Okay, we don't use logs. We use logs when x is in the exponent. All right, is that okay? All right, so now I'm going to convert the other way. The other way is just as simple. You keep the base and you switch y and x, except now I'm writing as an exponent. So the base is 3, that's the base of the exponent. And you switch y and x. So 3 cubed would equal 27. That's your exponential form. Okay, keep the base, switch y and x. Well, this guy, the base is 36. So 36 to the 1/2 would equal 6. Okay. So here the base is 2, switch y and x. So 2 to the negative 3 equals 1/8. So it's all about keep the base, switch y and x. All right, even when there's x's, it's still the same. So this guy would be 3, switch y and x. So 3 to the x equals 81. All right, base is x. So here I'm going to flip this. So x cubed equals 1,000. Okay. And here, keep the base, switch y and x. So 4 to the 1/2 equals x. Okay. All right. So converting back and forth, it's always the same thing. Keep the base, switch x to 6, switch the 2. All right, is that all right? Okay. All right, so why do we do this in the first place? Well, we do it to solve equations. We're going to work with, you can work with logarithmic equations or exponential equations. When you have a log, you can't solve that algebraically, so you have to get rid of it. You get rid of it by writing it as an exponent. So like this equation here, I couldn't solve that, but I could write it as an exponent. So the base is 3. So I have 3 to the 5th equals x, and that's just a number, right? I can solve it because I got rid of the log. 3 to the 5th, if you plug it in the calculator, I don't remember what it is, 243? Yes, 243. All right, so I've solved that equation by writing it in exponential form. So to get rid of a log, you can write it in exponential form. So like this guy here, I'm going to keep the base. The base is 2. I'm going to switch these. So 2 squared equals x minus 3. And this is something that I can solve now, right? Because 2 squared is otherwise known as 4. And then if I add 3 over, I'm going to get x is 7. Okay, so you can get rid of a log by writing an exponential form. What that does is help you solve log equations. Okay, all right. Now, this is the one thing to keep straight. All right, logs solve exponential equations. Exponential equations have x upstairs. So if I have x squared equals 6 or whatever, that is not something I'm going to use a log for. But if I have 2 to the x equals 6, this requires the use of a log. Use a log. Okay, when the x is upstairs, it needs to come downstairs. So I'm going to rewrite these equations in logarithmic form, and I'll be able to solve them. So here the base, I'm going to use a log. The base is 2, and I'm going to switch these guys. So log base 2 of 17 would equal x, right? So that's just a number. That's a number I can plug in my calculator. So I'm going to do that. I'm going to do alpha. Let me get out of this. All right, alpha window, log base 2 of 17. And I get 4.087-ish. Okay, so that the logs help me solve an exponential equation. So like here the x is upstairs. I'm going to write it as a log. So the base is 4. Switch these guys. So log base 4 of 64 equals x plus 2. Now you could plug that into a calculator, but I know what it is. It's 3. I just plugged it into a calculator. Just pretend I did. So then I minus 2 and I get x is 1. Just to show you, you can check that. If I plug 1 in here, up here, I get 4 to the 1 plus 2 is 3. And yeah, that equals 64. So I know I did it right. Okay, so I checked it. Okay. All right. So we're going to go down and we're going to, now that's the end of their stuff. I did it this way for a reason, because then in our stuff, they do some really weird stuff. They just use one log rule. There are actually 3 that you want to know. I'm going to write them down because you should know them. But I'm going to write it down here. So I'm going to flip down to 10.4 in our packet, which may take me a second. Let's just do it this way. So oh, back. All right. All right, so there's actually 3 rules you want to know, and I actually did 4, but first thing I would tell you that, you know, we talked about it briefly, but the log of 1, any base, is always 0, because anything to the 0th power is 1, all right? I would know that. It's helpful to know that. And it's helpful to know you can only take logs of positive numbers. Now, if there's 3 rules that you're going to use, not just the one that they've written here. I don't care what the base is. It could be log, ln, it doesn't matter. But these are exponent. They're kind of like exponent rules, because when you multiply exponents, you add the exponents. So this is the log of a plus the log of b. These are the only 3 rules that you can use. That's 1 rule. 2. The log of a over b, when you divide exponents, you subtract the exponent. So it's log a minus log b. And the last one is the one that we're interested in. If you have the log of a to the r, let's just call it a to the r. So let's take a power to a power, you multiply them. So the r comes out front. This r comes out front. So it's r times the log of a. Okay, so these are your 3 kind of basic log rules that you use all the time. And I don't think they're bad to memorize, because multiplication turns into addition, division turns into subtraction, and the r comes out front. So that's kind of how I have them memorized. All right, so she has these basic rules, and there's really no reason to go through all this. Just pull the power out front. So if I want to take log base 2 of x to the 5th, all I got to do is take that 5 and pull it out front. So it's 5 log base 2 of x. So the power comes out front. That's the power rule. I'm going to do a couple more of product and quotient, because I don't know why they didn't do them. Log base 2 of 5 cubed. So it's always the same. When you have something to a power, the power comes out front. So it's 3 times log base 2 of 5. So the base always stays the same. Never mess with the bases of the logs. They never change. All right, so this power comes out front. So it's 10 log base 2 of 4. Again, these are kind of repetitive. So I pull the 7 out front here. It's 7 log base 2 of 8. So when you have a power, just pull the power out front. All right. And this can help you when you're solving equations. I'll just leave it there because that's 1324. All right, or 1325. So I'll just do this last one. So the 20, again, the power comes out front. So it's 20. Wow. Log base 3 of 15. Okay. Well, is the 5 going to come out? Oh, okay, there it is. All right. So just to keep in mind those other 2 rules, when you have a product, if I have something like the log of 3x, the product turns into the sum. So that would be the log of 3 plus the log of x. All products turn into sums. And the quotient, when I'm dividing, let's say I have 3 over x. It's the top minus the bottom. So it's log 3 minus log x. Okay. So these are your basic log rules you want to kind of keep a handle on that you may need, okay, in 1325. All right. I think that's it. Yeah. Okay. Any questions about anything? Are we good? All right. So we will finish, like I said, 10.4 you have the ability to do now. We'll finish 10.5 on Thursday, talk more about the final. The final should be the 9th and 10th unless that email infects me. I just don't know whether I'm a STEM class or not. I don't think I am, but I don't know. All right, but I'll let you know if anything changes, okay? Feel free to start taking that practice final. I've already opened it up, so feel free to take that practice final and start working towards your final if you want, okay? All right, any questions? All right, we're good. Okay. Have a good 2 days. I'll see you guys on Thursday.